Here's a brief presentation relating to simple bending and the sizing of beams. In a previous presentation, we considered simple bending and reviewed the engineer's bending theory. In this presentation, we're very slightly going to modify the application of the engineer's bending theory with the purpose of sizing I-section beams. So let's consider a beam made from elastic material and subject to a bending moment, capital M. This is shown in figure 1. Here's our beam, and it's subject to bending moment applied at the ends here. When a beam is being bent about its neutral axis, we have one side in tension and one side in compression. Such a beam configuration can be analysed in simple bending by employing the following expression known as engineer's bending theory, EBT, which is shown on the next slide. Here's engineer's bending theory, stated without proof, where capital M is the bending moment that's applied to the beam, and within this presentation we will calculate that from standard tables. The I in the equation is the secondary moment about the neutral axis, and that relates to a bend stiffness property. The lowercase sigma here is the bending stress. The Y is the distance from the neutral axis to the extreme fibre that's under stress. In our case, that would be the extremities of the beam section. E is the elastic modulus, or the Young's modulus, and R is the radius of curvature of the neutral axis of the beam. Now, in the previous presentation, we used engineer's bending theory as stated above to find various parameters, whether that was bending stress or maximum bending moment that could be applied, or the second area moment required, the radius of curvature, etc. In this presentation, we're actually going to simplify engineer's bending theory to a three-variable equation, as shown on the next slide. Because in this particular presentation, we are purely going to size beams. We're going to select a particular beam from standard tables of universal beams, and we are given a permissible stress, and we have a maximum moment applied. You'll see this approach on the following slides. Let's consider the elastic section modulus, usually given symbol Z. The quantity I divided by Y max, where Y max is the furthest distance from the neutral axis to the extremity of our section, is called the section modulus symbol Z. So in calculating the strength of a standard steelwork section, for example, we can simplify engineer's bending theory as the bending stress sigma is equal to the bending moment divided by the minimum section modulus, where the minimum section modulus is equal to the second area moment I of our section divided by the maximum Y distance. So in essence, simply referring to these two parts of the simple engineer's bending theory, and we're modifying them in terms of stress is equal to M upon Z. Just to show you the rearrangement of the engineer's bending theory, considering the M upon I is equal to the stress upon Y, we can rearrange that for the stress is equal to the M multiplied by the Y divided by the I. That could be written as M multiplied by the Y upon I, and we note that section modulus Z is equal to I divided by Y. So we could then rewrite the above equation as M multiplied by 1 upon Z, because Y divided by I is the reciprocal of Z. And so that forms the equation that the bending stress is equal to the M divided by Z. Within these calculations, we'll refer to typical permissible stresses. In the formula above, sigma is the bending stress, and within our calculations, we will be given a permissible or a working stress. For commonly used structural steel, the permissible stress is around 165 newtons per millimetre squared. For timber, the permissible stress ranges between 3 and 12 newtons per millimetre squared. Also, within some calculations, a factor of safety will be stated. Factor of safety is defined as the maximum allowable stress, and that's either the yield strength of the material or the ultimate tensile strength, and the question will state which to use, divided by the permissible or the working stress, the sigma value. Here's a typical stress-strain diagram for structural steel. Stress is plotted on the vertical axis in newtons per millimeter squared. Strain is plotted on the horizontal axis. And for a typical structural steel, the yield strength is around 275 newtons per millimeter squared, and the ultimate tensile strength, or the UTS as it's sometimes referred to, is around 430 newtons per millimeter squared. Either the yield strength or the ultimate tensile strength can be used in the factor of safety formula as the maximum allowable stress. Notice that this range between 0 and 275 newtons per millimeter squared is the permissible or working stress range within the elastic region. Let's consider types of loading. Two types of applied loading to the beams will be considered within these notes. The first is concentrated point loads. These act at one specific point on the beam. And type 2 will be uniformly distributed loads, UDLs as are sometimes referred to for convenience, and they act over all or a portion of the beam span. Note that UDLs are generally specified in newtons per meter or newtons per millimeter. Of course, beams can be subject to a combination of point loads and uniformly distributed loads. And this will occur in some of the questions we're going to analyse in this presentation. Let's consider types of beams. So within this presentation, beams can be supported in the following ways. One, they can be simply supported at both ends. Simply supported beam shown here. Bridge structure with a lorry, in which the lorry is applying some concentrated point loads to the beam through the contact of the wheels on the bridge, and the bridge is reacted at either end, so it becomes a simply supported beam. And the second type of beam we'll consider is a cantilever beam. This is typically a diving board beam. In the scenario shown here, we could have a point load applied at the end, and there would be a reaction here where the diving board is considered to be fixed in rotation here, so a fixing moment, and also a vertical reaction will be applied at this location as well. So for our simply supported beam, having a point load in the middle, the midspan, it can be shown that the maximum bending moment at this midspan position is PL divided by 4. P is the applied concentrated load, L is the length of the beam. If we have a UDL along the entire length of the simply supported beam, it can be shown that the maximum bending moment occurring in the middle, at the midspan, is omega L squared divided by A. Omega is the UDL in this case. And of course we can have the combined case of the point load applied in the middle and the uniformly distributed load along the entire length. So in this case the maximum bending moment will be PL upon 4 added to omega L squared divided by 8. And that calculates the maximum bending moment at the midspan here. For the cantilever beam, a similar approach. If we have the point load applied at the end, then the maximum bending moment at the wall in this case will be P multiplied by L. If we have a UDL along the entire length of the cantilever beam, omega here, then the maximum bending moment at the wall will be omega L squared divided by 2. And again, if we have a combined case with the concentrated point load at the free end of the cantilever beam, the UDL along the entire length of the beam, the maximum bending moment is P multiplied by L plus the omega L squared divided by 2. So that encapsulates the beam configurations and the loading conditions we will consider within this presentation. Here's a worked example. Example 1. The cantilever beam shown in the sketch is used to support a bogey. Here's the bogey. That's attached to a hoist that can move along the lower flange of the cantilever beam. The beam length, L, shown here, is 3 meters, and the maximum weight, P, that is to be carried is 1.5 kilonewtons. And that's to be located at the free end of the beam. That's the worst scenario, when the bogey is at the free end of the beam here. If the permissible bending stress in the universal steel beam is limited to 75 newtons per millimeter squared, we've got to determine the minimum I section that's strong enough for the loading stated in the question. We'll refer to British Standard 4 extracts for universal beams, and we'll assume that the local flange bending is not critical. In other words, this flange here doesn't locally bend. We're going to just look at the overall bending of the I section. So from the question, we can extract the beam length, L, it's 3 meters. I'm going to work in millimeters here, so that's 3,000 millimeters. The weight at the free end, or load P, shown here, is 1500 newtons. Is 1.5 kilonewtons. I've written that as 1500 newtons. And the permissible bending stress given in the question, lowercase sigma, is 75 newtons per millimeter squared. Example 1 continued. So the first thing we need to do is to calculate the maximum bending moment that occurs in the beam. And for a cantilever beam, we know from our previous slide that will occur at the wall, and it's given as P multiplied by L. The bending moment diagram for the cantilever beam will look like this, with the maximum bending moment at the wall here. So the maximum bending moment, which will occur at the wall here, is 1500, that's the force P applied at the free end, multiplied by the length of the beam, that's in millimeters, so that's 3000 millimeters, multiplied by the length of the beam, which is 3000 millimeters. So the maximum bending moment at the wall is 4.5 times 10 to the 6 Newton millimeters. In step 2 here, we're going to calculate the minimum elastic section modulus, Z value for the beam. So from the equation, maximum bending stress is equal to M divided by the minimum Z value. So rearranging, Z is equal to the maximum bending moment from above divided by the permissible stress. So from above, that's 4.5 times 10 to the 6 Newton millimeters divided by 75 newtons per millimeter squared as given in the question for the permissible stress. That evaluates to 60,000 millimeters cubed. What you will notice in a moment is that in our standard tables of BS4, they will actually state the section modulus in terms of centimeters cubed. So we will always need to convert from our millimeters cubed to centimeters cubed. So to convert section modulus from millimeters cubed to centimeters cubed, I'm going to use unity brackets, something we considered in a previous presentation. So 60,000 millimeters cubed multiplied by my unity bracket. In this case, 1 centimeter divided by 10 millimeters is unity. Remember, these are termed cancelling unity brackets. We have to cancel the millimeters on the top with the millimeters on the bottom to leave us with centimeters. Don't forget, in this case, we have a cube term to consider, so we have to cube the unity bracket. So essentially here we have 60,000 divided by 10 cubed, which is 1,000, so that becomes 60 centimeters cubed. So what we will do now is consider BS4, extract relating to universal beam sections. These I section beams is shown here on the right hand side, and we'll choose a serial size that's suitable for a minimum section modulus of 60 centimeters cubed. We will always consider our beams to be bending about the XX axis here, so it's the section modulus about the XX axis we want to read from the BS4 tables. The following slide shows an extract of such a table. So here's our universal beam section extract, BS4. I'm using an old standard here. Obviously, if you're undertaking these calculations for real, you would refer to the most recent standards and the most up-to-date sections. But I'm just illustrating the process of sizing a beam here. So I'm using an old standard for reference. So from this extract, on the left-hand side, I have what are termed serial sizes of beams and also the mass per meter of the respective beams. That's how we designate a beam. If we were to buy a beam, we would state the serial size and the appropriate mass per meter. The column we're interested here is the elastic modulus column. We need to be careful here because sometimes we refer to the Young's modulus as the elastic modulus. In this particular standard, the elastic modulus is the section modulus or the Z value, so be very careful here. And remember, we're always bending about the x-axis, that's the stiffest axis of the universal beam. Notice the elastic section modulus values in BS4 or in centimetres cubed. From our previous slide, we calculated we needed a minimum of 60 centimetres cubed. So scanning this column, the most appropriate section is actually the last section at the bottom here. That has 75 centimetres cubed. So we will choose the section 127 by 76 millimeters, having a mass per meter of 13 kilograms per meter. So here's our chosen section, designated as 127 by 76 millimeters by 13 kilograms per meter mass. That's a section modulus of 75 centimeters cubed. So larger than what we need, but in the right ballpark. And that's the process we're going to essentially undertake in all the questions. With the beam configuration we're given, we'll work out the maximum bending moment. From essentially engineer's bending theory, we'll find the minimum section modulus. We will convert our section modulus from millimeters cubed into centimeters cubed. And then we will scan our extracts of BS4 to find the appropriate section. Question 1. A large timber beam is designed to withstand a maximum bending moment of 14.63 times 10 to the 6 Newton millimeters. The permissible bending stress is not to exceed 7 newtons per millimeter squared. We've got to, in part A, calculate the minimum section modulus Z required for the beam in millimeters cubed. In part B, we're asked to convert the section modulus from millimeters cubed to centimeters cubed. And part C, if the timber beam is now to be replaced by a single universal beam, we've got to select an appropriate UB from table 3 of our notes, which is the extract of BS4. The answers are stated in the brackets for reference. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so, but the full solution is shown on the following slide. So question 1, we're given a large timber beam, has to withstand the maximum bending moment of 14.63 times 10 to the 6 Newton millimeters, so we've got the value of M in this case. And we've got the permissible bending stress for the timber beam is 7 newtons per millimeter squared. So the sigma 7 newtons per millimeter squared. So the first thing we need to do is to calculate the minimum section modulus, the Z value. So from the formula, the maximum bending stress is equal to the maximum bending moment divided by the minimum section modulus. So rearranging, the Z is M divided by sigma. So inserting the values from above, we get a minimum section modulus of 2.09 times 10 to the 6 millimeters cubed. So for the timber beam to withstand the bending moment applied, that's the Z value we need to use. Question 1 continued. Second part of the question, we need to convert the section modulus from millimeters cubed to centimeters cubed. So essentially our Z value in millimeters cubed is divided by 10 cubed, divided by 1,000 in other words. So the minimum section modulus is 2,090 centimeters cubed. So the final part is to refer to our British Standard Universal Beam section and choose an appropriate beam section. So we're now referring to our extract of BS4 for universal beams. And as usual, I'll scan the section modulus column here. Remember, we're always bending about the XX axis. Scanning down the column, the most appropriate section appears to be this one here that has a section modulus of 2,298 centimeters cubed. We want a minimum of 2,090 centimeters cubed. So now reading across the left-hand column, we find that's a serial size of 533 times 210 millimeters by 101 kilograms per meter. So the actual section modulus we'll be using is 2,298. Just notice for reference, that's approximately 10% larger than required. So that seems a reasonable universal beam section to use in this case. Question 2. A simply supported beam is 10 meters long, carries a concentrated point load of 150 kilonewtons at its midspan. If the permissible stress due to bending is limited to 70 newtons per millimeter squared, we have to select a suitable universal beam from standard tables, which has least mass in this particular case. The answer is shown in the brackets here. And if you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so now, but I'll work through the full solution on the following slide. So question 2, here's the solution. Extract the information from the question. We've got a simply supported beam. It's 10 meters span, so converting that to millimeters, that's a span length L of 10,000 millimeters. Carries a point load in the middle of 150 kilonewtons, 150,000 newtons, and that's in the center of the beam. We're also given the permissible stress, and that's 70 newtons per millimeter squared. The first thing we need to do is calculate the bending moment. I've sketched the bending moment diagram, the maximum in the middle shown here. So the first thing we're going to do is to find the maximum bending moment. We know from our previous tables the maximum bending moment for a simply supported beam occurs in the middle, and it's PL divided by 4. In this case, that's 150,000 newtons multiplied by 10,000 millimeters divided by 4. So 375 times 10 to the 6 Newton millimeters. That's the maximum bending moment at the midspan of the beam. Next, we need to find the minimum section modulus, the Z value. So from our formula of the permissible stress is equal to the maximum bending moment divided by the section modulus, we rearrange the section modulus Z is the M divided by the sigma. Evaluating, we need a minimum section modulus of 5.37 times 10 to the 6 millimeters cubed. Question 2 continued. So as always, we need to convert the Z from millimeters cubed to centimeters cubed. Basically, we divide by 1,000. So the minimum Z we need is 5,370 centimeters cubed. We now refer to our universal beam table. This question 2 continued. Here's our table. Scanning down the Z column, the section modulus column. We're trying to find a section modulus of 5,370. And I can see here we've got 5,385 at this location here. And reading across, that's a serial size 762 by 267 by 173 kilograms per meter. So that's our chosen serial size here. And the Z is 5,385 centimeters cubed. Question 3. A simply supported beam, 3.5 meters span, carries a concentrated load of 60 kilonewtons at its center, at its midspan. The working stress is limited to 165 newtons per millimeter squared. We have to choose an appropriate rolled section I-beam from our standard tables. In part A of the question, we have to choose the universal beam with the least mass per meter. And in part B, the universal beam with the least depth. The answers again are shown in brackets here. If you feel you can attempt this question without further assistance, I'd encourage you to do so. But I'll show the full work solutions on the following slide. So question 3, here's the solution. Extract the information from the question. We have a simply supported beam with a 3.5 meter span. Here's my simply supported beam sketched. My length, my span is 3,500 millimeters. I'm working in millimeters here. We have a concentrated point load of 60 kilonewtons. So my point load P is 60 times 10 to 3 newtons. And the working stress, or the permissible bending stress shown here, is 165 newtons per millimeter squared. That's extracting information from the question. Question 3, solution continued here. So the first thing we need to do is to find the maximum bending moment. And again, I sketch my bending moment diagram here, and the maximum bending moment occurs in the middle. We know from our previous work to find the maximum bending moment in a simply supported beam, it's PL divided by 4. Inserting the values from above, the maximum bending moment this time is 52.5 times 10 to the 6 Newton millimeters. So next step is to find the minimum required section modulus, the Z value. We know that Z is equal to the maximum bending moment M divided by the permissible stress sigma. From above, our maximum bending moment is 52.5 times 10 to the 6 Newton millimeters, shown here. And we divide that by the permissible bending stress, 165 newtons per millimeter squared, shown here. That evaluates to a minimum Z value of 318.2 times 10 to the 3 millimeters cubed. Question 3, solution continued. Now to convert our section modulus Z value from the millimeters cubed in centimeters cubed, so simply dividing the above Z in millimeters cubed by 1000, have the value in centimeters cubed, so the minimum Z value is 318.2 centimeters cubed. Now the question wanted us to find the least mass section and the least depth section. So if we refer to the universal beam section, is the extract of universal beam section. If we scan down the section modulus column about the XX axis, 318.2 is the minimum section modulus we need, so we can find a 351 centimeters cubed section, which reads a serial size of 305 by 102 by 28 kilograms per meter. So that's the first section we've chosen. And also I find another section that has a section modulus of 353.1 centimeters cubed, which again is suitable as we're looking for 318 centimeters cubed. So reading off that serial size, I have 254 by 146 by 31 kilograms per meter. So we can answer the question. We have a least mass section. The 305 by 102 by 28 kilograms per meter is least mass, but it has a bigger depth than the 254 by 146 by 31 kilograms per meter, which is the least depth section. So that's what's shown in the table. Least mass section, 305 by 102 millimeters by 28 kilograms per meter. That was a Z value of 351 centimeters cubed. And the least depth section chosen is 254 by 146 millimeters by 31 kilograms per meter. And that has a Z of 353 centimeters cubed. So there's our least mass and our least depth sections chosen. Question 4 is a cantilever beam of length 260 centimeters, careful with the unit there, and it's designed to withstand a point load of 0.4 meganewtons at its free end. The permissible stress given this time is 150 newtons per millimeter squared. We've got to determine the suitable rolled eye section from standard tables, and again, two parameters here, A having least mass per meter and B least depth. Again, answers are shown in the brackets for your reference. If you think you can attempt this question, I'd encourage you to stop the presentation and do so, but I'll work through the full solution on the following slide. Question 4, the solution. The cantilever beam length is stated as 260 centimeters, so that's L here, and I've converted my 260 centimeters into millimeters to 2,600 millimeters. Stated that the point load at the free end of the cantilever beam is 0.4 meganewtons. So my P value here, point load of 0.4 times 10 to the 6 newtons. The permissible bending stress is stated as 150 newtons per millimetre squared. So sigma 150 newtons per millimetre squared. So the first thing we'll do is calculate the maximum bending moment in the beam, and that of course occurs at the wall over here, at this end here. From our previous work, the maximum bending moment in a cantilever beam is P times L. So in this case, inserting the values, that's 1040 times 10 to the 6 Newton millimeters. Question 4, solution continued. Step 2, we're going to calculate the minimum required elastic section modulus, Z of the beam here. So Z is equal to the maximum bending moment divided by the permissible stress. Inserting our values from the previous slide, our minimum section modulus is 6.933 times 10 to the 6 millimeters cubed. Next step, we're going to convert that into centimeters cubed. So we essentially divide the above value by 10 cubed by 1000. So the minimum required section modulus is 6,933 centimeters cubed. Scanning the universal beam extract here, again reviewing the section modulus column. We need a minimum of 6,933 centimeters cubed, so my first section chosen here, that has 7,210 centimeters cubed. So my least mass section here will be a 914 by 305 by 201 kilograms per meter section. And reading further down the column, I can also use this section, 7,986 centimeters cubed. So my least depth section will be an 838 by 292 by 226 kilograms per meter. There's my section. Least mass, 914 by 305 millimeters, 201 kilograms per meter. Section modulus is 7,210 centimeters cubed. And my least depth in this case is an 838 by 292 millimeters by 226 kilograms per meter. That was a section modulus of 7,986 centimeters cubed. In question 5, a simply supported beam spans 4 meters to which a central point load of 250 kilonewtons is applied at the midspan. And that's combined in this case with a UDL of 50 kilonewtons per meter that runs along the entire length of the beam. A standard rolled I-section beam is to be used with a factor of safety of 4, and that's applied against its failure strengths, which is taken to be the material's ultimate tensile strength UTS. If the UTS of the structural steel is 500 newtons per millimeter squared, we've got to select a suitable section from the standard tables having A, least mass per meter, and B, least depth. If you think you can undertake this question without further assistance, I would encourage you to do so. There is a hint shown in the question related to calculating the permissible stress given the UTS and the factor of safety. And as always, the answers are shown in the square brackets here. We'll show the full solution on the following slide for reference. So it's question 5. So extracting the information from the question. The beam length is 4 meters. So the length here I've written in millimeters, 4,000 millimeters. The central point load is 250 kilonewtons, so my P is 250 times 10 to the 3 newtons. And the UDL across the entire span is 50 kilonewtons per meter. So this is my omega. So that's 50,000 newtons per meter, or in terms of millimeters, which I'm using here, that's actually 50 newtons per millimeter. For ensure the conversions there, you can refer to use of unity brackets we outlined in a previous presentation. Just for reference, here's the conversion using a unity bracket of a UDL in newtons per meter to a UDL in newtons per millimeter. Remember from our previous presentation, these are cancelling unity brackets. So as I have the meters in the denominator of the UDL, then the unity bracket has to have the meters in the numerator. So the meters cancel. These are cancelling unity brackets. So essentially my 50,000 newtons per meter becomes 50 newtons per millimeter. There is a separate presentation on the use of unity brackets. We're also given in the question a factor of safety of 4. That factor of safety is against the UTS. We're given the UTS for this particular steel. The UTS is 500 newtons per millimeter squared. So first off, I will calculate the permissible bending stress. So the permissible bending stress, or the working stress, sigma, is the ultimate tensile strength divided by the factor of safety. So in this case, 500 divided by 4. So 125 newtons per millimeter squared is the permissible bending stress. Question 5, solution continued. So we've got a combined loading case here, the point load in the middle and the uniformly distributed load, the omega, along the entire length. So, step 2 here, to calculate the maximum bending moment due to load P. Maximum bending moment would be PL upon 4 from our previous table. The point load P is 250 times 10 to 3 newtons. That's multiplied by the length of 4,000 millimeters divided by 4. So 250 times 10 to the 6 newton millimeters is the bending moment due to the point load at the center of the beam. And step 3 shown here to calculate the maximum bending moment from the UDL. Of course, that occurs at the midspan as well. So that maximum bending moment is omega L squared divided by 8. The omega is 50 newtons per millimeter. The length 4,000 squared in this case divided by 8. So 100 times 10 to the 6 newton millimeters. So step 4, to find the maximum bending moment at the midspan, we simply summate the above values. So the maximum bending moment is equal to the bending moment from the point load, 250 times 10 to the 6 newton millimeters, added to the bending moment from the UDL case, so add 100 times 10 to the 6. So the maximum bending moment is 350 times 10 to the 6 newton millimeters. Question 5, solution continues. So part 5, we're going to find the Z value, which is the maximum bending moment divided by the stress. So from the previous slide, maximum bending moment is 350 times 10 to the 6 divided by the permissible stress, 125 newtons per millimeter squared. So 2.8 times 10 to the 6 millimeters cubed is the minimum section modulus we need. Step 6, converting the section modulus from millimeters cubed to centimeters cubed, divided by value by 1,000. So 2,800 centimeters cubed. That's a minimum section modulus we're allowed to use. Again, from our universal beam table, considering the section modulus column here about the x-axis, if I scan down the column, I need 2,800 minimum section modulus. I can see I've got a 2,879. So a 610 by 229 by 113 kilograms per meter will be my minimum mass section. Scanning further down the column, I can see this section here is essentially a valid section. And scanning further down this column, I find this section here actually has 2,799 centimeters cubed. We're looking for 2,800, but that would be reasonable in this case with the high factor of safety. So my least depth section is a 533 by 210 by 122 kilograms per meter. And there's a summary of my sections for least mass and least depth. For reference, here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.